Now we're going to do one where you're given a middle in between probability, and we're going to have to do this twice. So the weights of adult male huskies are normally distributed with a mean of 55 pounds, standard deviation of 6. And we want to know the middle 85% of huskies will weigh between what two weights. So we want to know what is the actual weight where we know in between is going to represent 85% of the huskies. So we need to get a z-score for the upper bound, and we need a z-score for this lower bound down here. So then we'll know, once we know those two weights, we'll know 85% of huskies will be between that lower and that higher weight. Now we need to figure out what are we going to type into a spreadsheet, because spreadsheets take left tail probabilities. So to get this lower bound, we need to figure out how much of the remaining percentages are in the upper tail and the lower tail that we're trying to cut out. Since we only care about the 85% in the middle, we're technically cutting out this red section below, the left tail, and that right section above, the right tail. So what I know is that if the middle of it is 85%, 100 minus 85, that means 15% of the data is left in the two tails combined. So I need to split up that 15 by 2, and I get that that left tail we're cutting off represents 7.5%, and the upper tail we're cutting off represents a right tail of 7.5%. Now, for my lower bound down here, we can literally just put in this left tail of 7.5%, which will be 0.075 when it's time to go to our spreadsheet. And that will get us the z-score we need that is connected with the lower bound, because that's the left tail. Now, to sort of think through what is the left tail up here, how much of the data is below that upper bound we're searching for? Well, that below it includes this entire 85% that we care about, plus the 7.5% tail that we're cutting out. So 85 plus 7.5, we are going to need to put in a 92.5% or 0.925 to get the upper bound. So I'm going to go take those two left tail probabilities, 0.925 and 0.05. So let me get these written down for us. So they're staring at us. So we got 0.075, 0.075, and then, oops, why didn't that go? Enter, Sorry, the iPad's a little bit trickier sometimes. 0.075. Well, let me just restart this real quick, or I'm just gonna go right below it because this should be, okay, well now it's working. And then the other left tail, so I know that the lower bound's left tail is 7.5, so that's gonna be 0.075. My upper bound left tail is actually 92.5%, so 0.925. So 0.925. And now let's go get the norm.s.inv for this first one, 0.075. Oops, where's the error? Maybe I need to close the parentheses. 0.075. Yep, there we go. And then down here equals norm.s.inv. And I'll put my next left tail, 0.925. And we'll get the z-scores. And you're going to notice they're the same exact z-score, but one's positive and one's negative. So it's going to be negative 1.4, that'll 40. That'll round up to negative 1.440. And this one is positive 1.440. So when the two tails we're cutting off are identical, like 7.5% and 7.5%, we should get the same exact z-score. One's positive, one's negative. And now we can plug those in one at a time. The mean plus the z-score times the standard deviation. The mean plus the z-score times the standard deviation. So let's do that real quick. 55 plus negative 1.440 times 6. We'll get a lower weight of 46.4 pounds. Then I'm going to go back up and make that a positive version of the z-score, and I'll get the upper bound, 63.4. So huskies that weigh between 46.4 pounds and 63.4 pounds will represent the middle 85% of the data.